So certain stars pulsate, and the speed at which they pulsate tell you how bright they are. So you look for stars, you say it's pulsating at a certain rate, so it must be that bright inherently. It looks that bright to me, so it must be that far away. If you do that, then you come up with the early 20th century model of the universe, which is actually the one that we use today. So, a couple of minutes on this. Edwin Hubble was a graduate student, and he was asked about measuring the distance to the Andromeda galaxy. Because the Andromeda galaxy is a fuzz, you can see it actually at the moment, late at night, still, it's a good time of the year to see it. You can see it with the naked eye. We now know it's 2 million light years away, which means we see it as it was 2 million years ago. But back in the early part of the 20th century, people didn't know how far away it was. No idea. So Hubble went and tried to figure out how far it was by actually looking at these Cepheids. So these Cepheid stars are in our galaxy. He said, I wonder if they're in this other galaxy, the Andromeda galaxy. Sure enough, he found some. He was able then to measure the distance to the Andromeda galaxy. And to use a technical term, he realized the Andromeda galaxy was very far away, much further than had previously been estimated. And he took the same approach, because if it works in our galaxy and it works in the Andromeda galaxy, and it's going to work everywhere. That's the assumption you make. And he found that the universe actually was really doing something really interesting, that it was expanding. So he tried to figure out how big is the universe, because we didn't know that, and he got a better handle on that. But for free, he got this whole new piece of information. The universe is expanding. We didn't know this before Hubble came across. Hubble didn't try to determine is the universe expanding, he just wanted to figure out how big it was. So that's an amazing discovery. He discovers roughly how big the universe is, and he discovers that it's expanding. So if something is expanding, and this line here shows, if you like, well, technically this is showing distance and speed and distance. I don't really know why, that's probably not relevant right now. But if you work back the difference in speed, you can use this slope. And I'm realizing here that I'm not going to explain this properly in the context of tonight, but you can use the fact that the universe is expanding in a general way, that if I do this, if you see you doing this, you think, okay, let me just run that backwards. And when I get to everything coming together, that must be the age of the universe. So if I know how big it is, and I know how fast it's expanding, then I can figure out when it must have started. So the other piece of information that Hubble got, 3 pieces. I mean, talk about lucky. You set out to do one thing, and you find 3 key pieces of information about your universe. Well, 2 that were totally unknown. 1, that it's expanding, and 2, how old it is. Because the universe had to come all from a single point at some time in the past, and although Hubble got that horribly wrong for various good reasons, that set about what I said at the beginning of the talk, 13.7 billion years. If you do what Hubble does and you map how far away things are and how fast they're moving, and you run the picture back, you get 13.7 billion years. That's an astonishing discovery. Only 100, 200 years after we realized the Earth wasn't the center of the universe. We've gone to having no idea how big the universe is, and to thinking we're at the middle of it all, to realizing we're a tiny speck in an enormous universe which is expanding and started out at some time in the past, so isn't infinitely old. Now, roll on to almost the 2 girls at the foot, you're almost old enough to remember this. But about 20 years ago now, so a little bit more, I'm realizing I have to amend my almost estimate. 2 groups set out to refine this expansion of the universe. They wanted to know, is the universe 13.7, is it 13.8, is it 13.5? What exactly, how fast is it? And they also want to know, is the universe expanding? And is it expanding at a constant rate? Is it slowing down? Most people felt it was probably slowing down, so that our universe was going to go sort of out and collapse back to a point and then start again, and so on. And this was kind of what was assumed. There was no strong basis for it, but it was kind of assumed. So people said, okay, that's great. So we figure out how the universe is expanding. So this is this slide. I've done it in reverse. I just realised I was looking at the wrong slide, so I have to go back to that other slide. So these two groups trying to figure out how fast is the universe expanding. So actually, the model that they were trying to figure out, or thought was most likely, is you start at a point, the universe gets bigger, and then it goes back to a point again. That's the one I just mentioned. However, another possibility is the universe expands and then gets no bigger, reaches a certain size and is always the same size forevermore. Another possibility is the universe gradually gets bigger, which is this one here. Or one that nobody predicted. I mean, nobody was talking about this. What these two groups found in 1998 is that in fact the universe has been getting bigger, but the rate at which it's getting bigger is getting faster. We are accelerating the expansion of the universe. So in the last 20 years, we've realized that our universe is literally blowing itself apart. And it truly is blowing itself apart. So at the moment, the atoms in your body hold themselves together. In quadrillions of years into the future, I just made that up, by the way, okay, that's not a real unit. But in quadrillions of years in the future, the stretch of the universe will rip even the atoms apart, so that the nuclei and so on that go together and the electrons around them will be ripped apart by the very fact that the fabric of the universe in which we sit will be ripped apart. But, and apologies for doing it in the wrong sequence, it doesn't really matter in a sense, but I just started the commentary in the wrong sequence. We also then were trying to figure out about how heavy the universe was. So we're trying to measure how much mass is in this galaxy. So we look here and you see, oh, there's a lot of light here. So there must be 100,000 million stars. So you know what the mass of the galaxy is. So what you can do a trick. You can measure how fast things are moving as you move out from the center. So if you go, as you move out, this is what we call 5 just units of distance. And then you measure how fast the stars are moving. So what we expect under Newton's laws is we expect the graph to go up. So the stars, as you move further out, should be traveling faster. And then as you travel further away, that should kind of level off. So when you're very far away from a galaxy, the stars very far away should be traveling at a constant speed. Well, whether you're that distance or that distance. Whether you're that distance or that distance, you're at roughly the same speed. But there's also a peak. You expect this to be the fastest the stars are moving. What happens is, you plot the curve, it does this. Now, even if you're thinking, I'm not really sure what he's getting at here, here's the thing. We can all see that this and this are not the same. So one theory predicts this. This is Newton's laws of motion, which I said are wonderful, and we should all celebrate. Job done. And then we find this, which doesn't follow Newton's laws of motion. So we start to look for lots of matter that might be out here. Because if there's a big load of dark stuff out here, which you can't see, and I don't want any applause, by the way, for my graphical abilities here. I think we can all agree that I've taken the rather expert course in Microsoft PowerPoint. But if we put lots of matter out here, this graph becomes this graph. So we think, there must be lots of matter way off out beyond the galaxy, what we call a halo. We go to look for it, and we can't find it. So we can't find this stuff, but we know that it's there because it's making this actually happen. The stars are actually following this, so there's something weird there. This is the dark the dark matter that I referred to at the very start of the talk. This expansion of the universe is the dark energy that we refer to. So dark matter is causing somehow our galaxies to rotate differently to the way they should. They're actually supposed to rotate that way, clearly, because they do. So should just means that that's what we expect them to. Dark energy causes our universe to accelerate in how fast it's expanding. A real surprise for us. So dark energy is blowing the universe apart. Dark matter is trying to stop this. So actually this dark matter that we showed there around the galaxy is trying to pull the universe back this way. Dark energy is trying to push the universe that way. And clearly, because of this graph here, you can see who's winning. It's the stuff that's pushing the whole universe apart is doing the winning. So the dark energy is winning. And the best bit of it all is we don't have a clue what this is. So I'm predicting that our two young scientists in the front row and our young scientists in the middle there will be the ones to figure out what this is all about. Because this is going to take a bit of time and effort to figure out what this is.